Okay, so today what we're going to do is we're going to talk about the meaning of probability. What do I mean by that? I mean, you hear the word probability, you hear the word chance. This thing has a 37% chance of happening. What does that really mean? Okay, why is it 37%? What does the number 37% chance mean? Why is it 37% chance instead of 39% chance? What exactly does the number mean? So that's what we're going to spend the whole day on. Okay, so when you get a probability number, what does the probability number actually mean? Okay, so first of all, I'm pretty certain that everybody knows what 100% probability is. So 100% probability means that whatever event you're looking at, it will always happen. It means that your event will for sure happen. It's going to happen for sure every time you run the experiment. Let me just give you, here, for sure happen. Let me underline this. Okay, so it'll for sure happen. 100% chance, definitely it will happen. A quick example to have in our heads is if you let's say you roll a die. Okay, so if you roll a die, what is the chance or what's the probability that the number you get will be less than 10? And the answer is 100% chance. Every time you roll a die, it will for sure be less than 10, the number, because all the numbers on the die are less than 10. So no matter what the outcome is, for sure the event of it being less than 10 will happen. So that's what 100% probability means. That event will always happen. Every single time you do the experiment, the event will happen. So I'm pretty certain everyone understands that. And then 0% probability, I'm sure everyone understands that as well. It means the event will never happen. It means that your event will never happen or never occur, no matter how many times you run the experiment. How many times you run the experiment. So another one, here, let me underline this, so it'll never happen. For example, if you're rolling a die, what's the probability you'll roll a negative number, okay? That has 0% chance or 0% probability. It'll never happen because there's no negative numbers on the die. Okay, that kind of thing. Okay, so 100% probability, I'm sure everyone understands that your event is always going to happen. Every time you do the experiment, it's going to happen for sure, guaranteed. 100%, it will not happen. Guaranteed, it will not happen, whatever the event is that you're looking at. Okay, so I'm certain everybody knows those two things. And then the other one that I'm pretty certain everyone understands is if you have two events with two probabilities. Let's say the probability of event E is 24%, and the probability of event F is 53%. What does this mean? It means event F will happen more often because it has a bigger probability than E. Then event F will happen more often than event E. E has a lower probability, lower chance. It's not going to happen as often as F is. So if you run the experiment a bunch of times, F is going to happen a lot, and E is not going to happen as much. For example, it could be like, so E could be the event that let's say you're going to draw a card from a deck of cards. E could be the event that you draw an ace, okay? And F could be the event that you draw a heart. Now, these would be the wrong probabilities, these numbers up here. But the point is, the probability of F is bigger than the probability of E. Here, let me actually go ahead and put the correct probabilities for these two events here. Actually, let's change this from heart to red. So then the probability of drawing a red card when you draw a card out of a deck of cards is 50%. And the probability of drawing an ace, if we do that on the calculator, let me do it real quick, 4 divided by 52 is like 7.7%. So that just means if you draw a card out of a deck of cards, red cards will come up often. So if you just drew one card out of deck cards a bunch of times, this will happen often. You'll get red cards often. You won't get aces so often. Okay, so lower probability, that event won't happen as often as the one with the higher probability. Okay, so I'm certain we know those three things. We understand what 0% means. We understand what 100% probability means. And if we have two events, the one with the higher probability has a higher chance of happening, meaning it'll happen more often than the one with the lower probability. When I say more often, I mean if you run the experiment more than once, if you run it over and over again, then the one with the lower probability won't happen that often, but the one with the higher probability will happen more often, okay? But now the question is, again, if I just give you one event, okay? So if I just say probability of event F is 38%, why is it 38% instead of 39% or 32%? Why exactly 38? What exactly is this 38 trying to tell us? Okay, and that's what we want to understand today. Okay, so let's go through that. So what does the probability number actually mean? So what does the number, okay, for the probability actually mean? Okay, now, there's a certain way I'm going to want you to write the answer. I'm going to give you the format in a minute. But what we're going to do right now is we're going to look at a bunch of experiments. We're going to look at the experiments that you guys did last time first. So you guys remember at the end of class last time, I had you guess some probabilities empirically. In other words, I didn't tell you what the probability was. You had to guess it. And the way you guess a probability is you run the experiment a bunch of times and you calculate the percentage of times your event occurred. So let me remind you of some things here. First, I got to pull up this file. So the first experiment that we did in class last time is there's a bag that has chips in it, poker chips. Now, I know we didn't actually have a bag, but we simulated having a bag of poker chips. And your job was to not look in the bag. You don't know the contents of the bag, but you were supposed to draw a chip out of the bag, put it back, mix them up, draw a chip again, put it back, mix them up, and try to guess the probability of drawing a blue chip. And again, because we're doing things online, there was no actual bag, so we simulated it on the computer. But that was the idea. So let me go ahead and click on this. And I want you to look at the data from the students from last class. So, okay, then it says everything over here. So the experiment is drawing a chip. So we're going to draw one chip out of the bag. Remember, the experiment in every probability problem, the experiment is the thing you're about to do, the thing you're doing. So we're about to draw a chip out of a bag. Okay, so that's the experiment. And the event is, after you draw the chip, you look at it and you see if it's the one you care about. What do we care about? I care if it's a blue chip because that's what I'm trying to find the probability of. So let's make sure that's clear. The experiment is draw one chip out of a bag. The event is, was it a blue chip or not? Now this is one student's data. Let's take a look. So remember, this column here, did the event occur? You were writing 0 if it didn't occur and 1 if it did occur. So this student on their first draw, they did not get a blue chip. Okay, so far the percentage of times they got a blue chip is 0 out of 1. 0 blue chips total out of 1 draw total. On the next draw, they did not get a blue chip again, so 0% up until the fourth draw. On the fourth draw, they did get a blue chip. The percentage of times they got a blue chip so far was 1 blue chip total so far out of 4 draws total so far, which is 25%. And then let's do it again. So on this fifth draw, they didn't get a blue chip. So what's the percentage of times they got a blue chip so far? Well, they got 1 blue chip total so far out of 5 draws. 1 out of 5 is 20. On the sixth draw, the student did get a blue chip. So what's the percentage of times they got a blue chip so far? Well, they got 2 blue chips total so far out of 6 draws, 2 out of 6, and it gives you this 33%. And on we go. So you look at these percentages on the right, and each one of them is a guess of the probability of drawing a blue chip. It's the percentage of times you got a blue chip so far, but each one is a better guess. The more times you draw, you get a better guess of the probability of drawing a blue chip. So after just a couple of draws, you're guessing the probability is 0%, and then it changes. And the idea is you want to look at all the numbers. I want you to watch as you scroll down the list. Let your eyes scroll down the list, okay? And the best guess this student had was 12%. Obviously, the more times you draw, the better guess you're going to have. So this student's guess was that there was a 12% probability of drawing a blue chip. Now, it turned out the way I set up the bags when I hand out the bags in class and the way I set up the app for the app on the website is that the probability of drawing a blue chip is going to be 25%. So the student wasn't that close. They got 12%, but it's okay. Why aren't they so close? Because they only drew 25 times. One thing you need to understand is the more times you draw, the better guess you're going to get. Okay, another thing I want you to notice is at the beginning, the numbers jump around a lot. 0, 25, goes up to 42. And then as you go down, one thing I want you to notice is the numbers still move around, but they don't move around as much anymore. Let's take a look at this graph. This is a graph of that student's data. Let's make sure you guys understand what this is, because we're going to see lots of graphs like this today. Okay, so the red line, okay, the height is the probability. So the red line is at 25%. The red line is the actual probability of drawing a blue chip. So I just put a line at 25%. The blue graph is those numbers you just saw. It's all the guesses, all your guesses for the probability of getting a blue chip. And the height is your guess. So, and then as you go to the right, you're drawing more times. So this is the first draw over here, and their guess was 0%. Second draw, their guess was 0%. Third draw, their guess was 0%. On the fourth draw, their guess is now 25%. Fifth draw, their guess is 20%. So as you move to the right, you're drawing more times. And the height of the blue, whatever height it's at, that's your guess. So at this point, your guess is that it's 40-something%, however high it is. Okay, so this, you see what's happening. So at the beginning, the numbers are moving around a lot. Okay, now this graph doesn't show everything I needed to show, but again, this is going to happen because we only drew 25 times. So I'm going to spoil the surprise and just tell you this is what's supposed to happen in every set of data if you do it enough times. Okay, at the beginning, it's going to move around all over the place, but as you go to the right, what will happen is the graph will level off. We don't see that here. It's just going down, 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 down. But eventually, if we do it enough times, the graph will level off like horizontal. It'll look roughly like a horizontal line, kind of like the red line. It'll look like a horizontal line, and it will level off to the red line. So actually, this blue graph will eventually hang around the red the whole time. Might be above it or below it, whatever, but it'll be very close. In other words, what I'm saying is, if you draw many times, so the right side is many times, the left side is just a few times, then the percentage of times you've got a blue chip so far will be very close, will be hovering around the probability, 25%. So it's going to level off, and it's going to level off to where the red line is. So now this is what I did. I just showed you one student's data, but now I took all the data from all the students in all my stats classes that did this experiment at the beginning of the week, and I put it all together so we could have more data. See, it's hard to get people to do much more than 25 times because we never have time. And if I said, guys, I want everybody in here to do it 1,000 times, you probably would be mad. It's too many. But let's watch. So I want you to watch as I scroll down, okay? I have like 1,000-something data numbers here. Take a look. What I want you to notice now is that the numbers are still moving around, but they're not moving around so much anymore. They're trying to settle down. They're trying to level off. And what are they trying to level off to? They're trying to level off to the actual probability, which we know is 25% because I set it up that way. So I'm going to scroll down faster. Okay, so watch the numbers. Okay, 22, 23. You know, you're never going to get something that's not in the 20s anymore. It's not going to go up to 40% again. It's really trying hard to level off to the right answer. Okay, and then, well, it turns out that after 1,624 tries, our best guess was 25%. Now, that's a super coincidence, okay? So don't expect us to get the exact answer when we're done. But it's supposed to be close. And you want to get closer, you do it more times. Let me go and take a look at the graph so you can get an idea. So this is the graph of all the data for all the students that did this. Again, the red line is at the actual probability of drawing a blue chip, which is 25%. The blue graph is the percentage of times we drew a blue chip so far. And again, notice at the beginning, it goes up, it goes down, it's moving around a lot. But when you go to the right, it's trying to level off, okay? It's trying to level off, and it's supposed to level off to the red line. You see we're a little below here, and then over here we're really close. But even, you know, 1,600 times is not enough times. But if we would have done this way more times, like, you know, 20,000 times or something, then you wouldn't even be able to see the difference much between the blue graph and the red graph. It'd be super close, almost lying right on top of it. It goes up a little, down a little, you know, but it's going to be hovering around the red graph. So here's what I'm trying to say. If you draw a chip from a bag many times, again, many times is this side. Just the first few draws is here. But if you draw many times, then the percentage of times you get a blue chip, which is the blue graph, is going to be very close. It's going to be about 25%, which is the actual probability. Okay. So now, you know, I'm going to ask you on a quiz to explain the meaning of this 25%, you know, so I'll tell you, on the quiz, I'll tell you. I'll say, okay, here's the thing you're doing. Here's the probability. What does it mean? Like, for example, I would say, when drawing a chip out of a bag, the probability of getting a blue chip is 25%. What does that probability mean? Okay, so I'm going to show you the structure of the answer. Okay, this is the structure of the answer. Okay, so I know you're paying close attention, but pay extra close attention now. Okay, so here's the structure of the answer. When you give the answer, you're kind of going to say it in 3 parts. First thing you're going to say is, if you run the experiment many times. So that's the first part of the answer, okay? Now, okay, let me finish it. So remember, you have to say many times because probabilities don't make sense if you just do something a few times, okay? So if you run the experiment many times, then your event will occur. The event will occur. That's the second part of the answer. And then the third part is going to be about, and you're going to put your probability in there, about blank percent of the time. So if you run the experiment many times, the event will occur. Here, let me put it in 3 lines so you can see the 3 parts. The event will occur about blank percent of the time. Make sure you put about, okay? Because you're not going to draw a blue chip exactly 25% of the time. It's going to be about 25% of the time. In other words, the blue graph is going to be super close to the red graph. It might not be exactly on the red graph, on the red line. It might not be exactly 25%, but it's going to be about. It's going to be very close to 25% on this side when you do it many times. Okay, so let me, here, I'll tell you what, I need the room. So let me space it out a little bit so you can see the 3 separate parts here. Okay, now here we go. Here is the first question, like the kind of question I can ask on the quiz. It'll say something like this. If you, okay, when drawing a chip from a bag, the probability of drawing a blue chip is 25%. What does this probability mean? Okay, so there would be like the question. All right, so this is a very important question and I will be asking this a lot. You'll see a question like this on the quiz for sure, on the next exam for sure, and it's gonna show up a lot. Understanding the meaning of probability is something we're gonna revisit over and over again in this class. So we gotta really make sure we can answer this question. All right, so I would like a volunteer to try to give me the answer. And again, you're gonna say your answer in this format. And then, you know, so when you say the answer, let me say this much. I'm not gonna want you to use the word experiment, okay? Don't say the word experiment. Say what the experiment is in the example that we're doing, okay? And then I also don't want you to say the word event. Say the event in the problem we're doing. So you have to recognize in the problem, what's the experiment, what's the event, and say those things and follow this format. And okay, somebody try it, and at least if you're, you know, if it's hard, let's at least try the first part. All right, so anybody who wants to volunteer, let me know. Anyone want to try?
I'll try.
All right, go ahead.
If you draw a chip from a bag, the probability of drawing a
Okay,
blue
let me stop you. Let me stop you. Okay. First of all, thanks for volunteering. The first person, it's probably the hardest on the first person. But I need to stop you for a couple things. First of all, when you say your answer, do not use the word probability and do not use the word chance, because I'm trying to figure out what these words mean. So when you're explaining your answer, don't use those words. That's the first thing. And the other thing is, in the first part that you said was sounding good, but you forgot to say many times. Okay, just say the very first part only and stop. Go ahead.
If you draw a chip from a bag many times.
Okay, that's perfect. Okay, okay. Can you try the second part now? So you said if you draw a chip from a bag many times, you said that. Then what?
Drawing a blue chip will occur about 25% of the time.
Yeah, that's pretty much perfect. Let me just say one other thing here. So, you know, when I write it like that, the event will occur. I prefer you don't say will occur, but you can if you want. It just sounds funny. You know, it's not like you're wrong. You're totally right. but it's kind of like this, okay? We don't speak like that in real life, right? It's like if I say, okay, I'm hungry, going to In-N-Out will occur, you know? Like, okay, everyone understands what I'm saying, but people don't talk like that, right? They'll say, I'm gonna go to In-N-Out, right? So I just want you to say, instead of saying getting a blue chip will occur, just say you'll get a blue chip. But again, if you say will occur, it's totally fine. But can you say your whole answer one more time?
If you draw a chip from a bag many times, drawing a blue chip,
Just say you will get a blue chip or you'll draw a blue chip.
okay, you will draw a blue chip about 25% of the time.
Perfect. Yeah. Okay. Let me get one more person to answer. Before you answer, let me just say some things. So sometimes when people say the first part, they'll say, if you draw a blue chip, but again, the experiment in this problem is not drawing a blue chip. The experiment is drawing a chip. And then you want to know, is it blue or not? So is it blue or not? Blue is the event. Okay, so just make sure we're clear. You didn't say that, but I'm just letting you know in case someone makes that mistake. Okay, one more person volunteer, please.
I can go. So if you draw a chip out of a bag many times, you'll get a blue chip about 25% of the time.
Perfect. Okay, let me go ahead and write it down now. So if you draw a chip from the bag many times, you will get a blue chip about 25% of the time. Okay, so that's how that goes. We're going to practice lots of these, okay? I'm going to give you different experiments, different probabilities. We're going to practice it a lot. That's the most important one. Now, normally in questions like this, I give you, I ask 3 kinds of questions, okay? That's the first one. That's the most important one. We'll change that to green. Okay, but these other ones, you're going to get them for sure on the next quiz, but they won't show up as often throughout the course as this first one. So really make sure you get the first one, but obviously get them all so that you know you do well on the quiz and all that. So, okay. So the second question I like to ask will go something like this. I'll tell you how many times you've drawn the chip, and you'll tell me how many times you'll get a blue chip. So for the second one, I'm not asking for percentages. I'm asking how many times. So I'll say something like this. If you draw a chip from the bag, let's say 80,000 times. Would you agree? Oops, got that wrong. 80,000 times. Would you agree that 80,000 times is many times? You definitely agree, right? That's a lot of times, okay? So if you draw a chip from the bag 80,000 times, so I'm telling you how many times you've drawn, and now I'm gonna ask how many times are you gonna get a blue chip. So if you draw a chip from the bag 80,000 times, how many times will you get a blue chip? Okay, so in this question here, again, I don't want a percentage. I'm giving you an amount of times that you're drawing, and you're going to give me the amount of times you're going to get a blue chip. Now, I'll just tell you how to do this one. The way you do it is you have to multiply the probability, which is 25%, by 80,000. Okay, and then there's one more thing you got to do, but let me just make sure everyone's clear on how to do that. So in case you're not clear, you take the probability. Here's the probability, 25%. You need to write the probability as a decimal. Okay. So in case people are unclear on how to do that, what you do is, first thing you do to write the probability as a decimal is you erase the percent sign, okay? And then you have to take the decimal point and move it 2 times to the left. If you don't see a decimal point like here, when there's no decimal point in the number, then the decimal point's at the very end, like this, okay? And what you need to do is you need to erase the decimal point and move it 2 times to the left. That's the decimal point. So that's 25% as a decimal. So you write the probability as a decimal, and then you have to multiply by 80,000 on the calculator. You do 0.25 times 80,000. When you're done, you're going to get 20,000. But that's not the answer. That's kind of like you calculate that and then give me the answer. So how many times do you get a blue chip? You don't write 20,000 times because it might not be exactly 20,000 times. So what you need to write is about 20,000 times. You don't have to write a whole long sentence for this answer, okay? But you just got to write 3 things: about, the number, and then times. About 20,000 times. Please do not forget the word about. It's almost as important as everything else. It's actually more important than everything else. The about is super important. And this is what would really happen. You know, if you draw a chip of like 10 times out of a bag, how many blue chips are you going to get? I have no idea. It could be any amount if you only draw 10. But if you draw 80,000 chips from the bag, that's many times. anyone who was willing to do that is going to get almost exactly 20,000 blue chips. So if you drew 80,000 chips out of a bag and you said, hey, Greg, I only got 10,000 blue chips, I'm going to say you're lying. There's no way. It's very easy to predict what will happen if you do it many times. It's going to be maybe not exactly 20,000, but pretty close to 20,000. It might be 20,050, you know, but it's no way it's going to be 30,000 kind of thing. Okay. All right. So please, for that one, make sure you don't give me a percentage as your answer. Make sure you put the word about. Okay. Let's go to the third question. Actually, let's do that one more time for practice, since this is the first time we're doing that. So I'm going to do 1B, just another 1B. I'll put a little apostrophe there for another one. So I'm just going to change the number. So if you draw, if you draw a chip from the bag 200,000 times, how many times will you get a blue chip? Okay, so there's the question. Again, I'm telling you how many times you're drawing. You're going to tell me how many times you get a blue chip. First thing you do is you have to multiply the probability. The probability is a decimal, is 0.25, times how many times you're drawing. You multiply. What do you get when you multiply those?
50,000.
50,000. Okay, and then tell me the answer to this.
About 50,000 times.
About 50,000. Yeah.
About 50,000 times. Don't forget the word about. Don't forget the word times. Yeah, that's how that one goes. Questions on the second kind of question that I could ask you. Anyway, we're going to do a ton of them, so don't worry. The third kind of question is going to go like this. Draw a chip from the bag infinitely many times. Let me stop there real quick. Some students are going to say, come on, Greg, you can't draw a chip infinitely many times. Okay, I'm going to say, okay, you're right. But you can, in a calculus sense, you can draw a chip infinitely many times. And then a student might say to me, hey, this is not a calculus class. Why are you making me think this calculus weird stuff? And my answer to you is, a lot of the stuff we do in here is actually calculus, it turns out. Okay, but I'm not teaching you the calculus lingo and all that stuff, but a probability. So if any of you know calculus, a probability is actually a limit. If you don't know what I'm talking about, don't worry about it, okay? But because of that, you know, we have to kind of sidestep the calculus words. So in a calculus sense, it makes sense to draw infinitely many times. So I will be asking you that question. If you draw a chip from the bag infinitely many times, now I'm not going to ask you how many times you're going to get a blue chip, because the answer is you're going to get a blue chip infinitely many times, and you're not going to get a blue chip infinitely many times. So I'm not going to ask how many times. I'm going to go back to a percent. I'm going to say, what percent of the time will you get a blue chip? Okay, so that'll be the question. Now the answer, let me explain how it's going to go. So let's look at the graph again. So here's the graph. Remember, this is a percentage of times you got a blue chip so far. And again, it moves around a lot at the beginning, but towards the right, it starts to level off, and it tries to level off around the red line, but it might not be exactly on the red line, and that's why we use the word about. But what I'm saying now is, if you could go to the right forever, remember, going to the right, the more you go to the right, the more times you're drawing. If you're drawing infinitely many times, it's like if you could somehow go to the right on this graph forever, then what would happen? The answer is the blue graph would be exactly on the red graph. It would line up perfectly. Okay, so what's the percentage of times you'll get a blue chip? It'll be exactly whatever the probability is. So when you say this answer, I would just go ahead and tell you this answer here. So the answer is, what percent of the time do you get a blue chip? You need to put the word exactly. Exactly 25% of the time. Okay, and that's how that one goes. Okay, so it's about 25% of the time when you draw many times for part A, but for this one, if I say you're going to draw infinitely many times, then you'll get a blue chip exactly whatever the probability is, exactly 25% of the time. And that's how that one goes. Any questions? And we're going to do lots of those, so let's move on. So that's data from one experiment that we did last time. So now we'll look at another one. So another thing that you guys were doing last time, so another experiment was you had a deck of cards. Again, I know you didn't have a physical deck of cards. We did a simulation on the computer, but let's just pretend we actually had a deck of cards. So you have a deck of cards, and the experiment was to draw the top two cards from the deck of cards. And then the event, after you draw the two cards, you look at it and see if the total was 20 or not, as in the game of blackjack. Okay, so that's this data here. This is one student's data right here. And again, let's make sure we're understanding what's going on. So the experiment is you draw 2 cards. And then the event, after you draw the 2, so the thing you're about to do is you're about to draw 2 cards, and then you're going to check if you got a total of 20. This student didn't get a total of 20 up until the 17th draw. Okay, and the 17th draw, they did get a 20. So the percentage of times they got a 20 so far was 0%, 0%. They never got a 20 up until the 17th time. On the 17th time, they did get a 20. What's the percentage of times they got a 20 so far? 1 time out of 17 draws, and that's what this 5.88% is. Okay, on the 18th draw, they didn't get a 20. What's the percentage of times they got a 20 so far? 1 time they got a 20 total so far out of 18 draws. That's what this percentage is. On the 19th draw, they got a 20 again. Percentage of times they got a total of 20 so far would be 2, because they got 2 20s total out of 19 draws. That's what this number is. And anyway, each number on the right here is a guess of the probability of getting a total of 20. And the more you draw, the better guess you get. At the end of the 25 draws this student did, their guess was that the probability of getting a total of 20 is 8%. Now, I told you that I calculated the answer. I didn't calculate it for you. I may do that in like a week or so. I may actually calculate it for you. But it turns out the actual answer is 10.25 or 10.26 or whatever percent. Okay, so that's not a bad guess. Their guess is 8%, and the actual answer is 10.25%. Okay, but still, that's only 25 times, so don't expect to get such a good guess. Let's take a look at the graph here. So same idea as the one I showed you before. The red line is at the actual probability of getting a total of 20. It's at 10.25%. The height of it is at 10.25. That height is telling you the probability. So red graph is the actual exact probability. The blue graph is the percentage of times the student got a total of 20 so far. And remember, it was 0% for a while. Remember, as you go to the right, we're drawing more times. So this is the first draw, second draw, third draw. And look, they're all 0%. The student got 0% for a while. Then it jumped up, came down a little, jumped up again, came down a little bit. Okay, at the beginning, these probabilities, the height of the blue graph, which is the percentage of times this student got a total of 20 so far. At the beginning, it moves all over the place. Okay. But if you do it enough times, it tries to settle down. Again, even this graph, you don't really see it settling down. So what I did was, again, I took the data from every student from all my stats classes and put them all together so we could have way more than 25 draws. And so I want to scroll down, and I want you to watch the numbers as I scroll down. Each of these numbers is a guess. Each of these numbers in this column here is a guess of the probability of getting a total of 20. And what happens to these numbers? The more times you draw, the less these numbers are going to move around. They're not going to move around as much anymore. They're trying to settle down, and they're trying to head towards the actual probability, which we know is 10.25. So these numbers are trying to get to 10.25, but it might take some time. And different experiments, it takes longer than others to get there. So let's go ahead and just scroll down faster and just watch the numbers. You see they're all 10, 11, 12. It's never going to go, to 5% again like it was earlier. It's going to try to get closer and closer to 10.25. At the end of the data for all the students, our best guess was 10.27. Now, again, that's super close to the right answer. Don't expect it to be that close that soon. Even 1,300 draws is not that many draws. So some people just got really, I guess I shouldn't really say lucky, but sometimes you're going to get a really close answer, and sometimes you have to draw more times before you get a really close answer. And here's a picture. And again, hopefully you're seeing this idea, but it's still not showing the best. And the reason is because, again, 1,300 draws is still not enough. But the blue graph is the percentage of times we got a total of 20 so far. At the beginning, it's all over the place, up, down, whatever. And then it's starting to try to level off. It's trying to level off. It's supposed to level off at where the red line is. It doesn't exactly look like it's doing that yet. It does kind of hit the red line towards the end. But again, don't expect that to always happen. But what I'm trying to tell you is if you did this way more than even 1,300 times, then on this side of the graph, when you've drawn many times, you won't really even be able to tell the difference between the blue and the red graph. They'll basically be lined up almost exactly on top of each other. All right. So again, the probability of getting a total of 20 when you draw 2 cards is 10.25%. That's the red line. The percentage of times you drew a 20 so far is going to be about 10.25% if you were to draw many times. So not the first few times. First few times, You have no idea how many 20s you're going to get, but if you draw many times, it's going to be right around what the probability is. That percent of the time you should be getting a total of 20. Okay, so now how will the question look on the quiz? Okay, so this first one would say, so again, in the sentence, I'm going to say, you know, here's the experiment, here's the event, here's the probability. Tell me what the probability means. So I guess in this one, I would have to say, when drawing 2 cards from a deck of cards, the probability of getting a total of 20 is, let's just say 10.26%. What does this probability mean? Okay, so that's the question. Let me get rid of these for now. Okay. So all I'm doing in this little sentence here is explaining what the experiment is, explaining what the event is, and I'm giving you the probability, and I'm saying, explain what the probability means. When you explain what it means, you have to say something like, if you do the experiment many times. Remember, you're gonna kind of go through this format here. Probabilities only really make sense if you do the experiment a bunch of times. What's the experiment in this problem? Drawing 2 cards out of a deck of cards. Not getting a 20. Getting a 20 is what you care about happening. You're not always going to get a 20. Sometimes you get a 20, sometimes you won't. So that's the event. So the experiment is drawing 2 cards. The event is do the 2 cards add up to 20? Okay. All right. So I want someone who hasn't volunteered yet to volunteer and try to explain the meaning of this probability. Let me read the question again. When drawing 2 cards from a deck of cards, the probability of getting a total of 20 is 10.26%. What does this probability mean? All right, someone answer it.
When drawing 2 cards from a deck of cards many times,
Yeah.
you will get a total of 20 about 10.26% of the time.
Yeah, let me write that down. I'm going to write it with the word if, but you can write when drawing, that's fine. If you draw 2 cards from a deck of cards many times, you will get a total of 20, about 10.26% of the time. Yeah, just like that. Okay, cool. Any questions so far? Someone might ask me, you know, Greg, you can't draw 2 cards from a deck of cards too many times because you'll run out of cards. Okay. And if you were thinking like that, then my answer to you is no, you'll never run out of cards, because this is what you're supposed to do. You're supposed to draw 2 cards, then put it back in the deck, shuffle, and then draw 2 cards again. Put it back in the deck, shuffle, and draw 2 cards again. You have to do it that way because I mentioned to you that you have to be able to repeat the experiment over and over again. And every time the conditions need to be the same as the other times. If you draw 2 cards from a deck and leave them out and then go to draw the next 2 cards, you're not doing the same experiment anymore. You're drawing from a different deck of cards. You're not drawing from a full deck. So it's kind of like, you know, you're drawing from a full deck, but then you're going to put it back and you're going to draw from a full deck again, kind of thing. All right, let's go to the next question. Again, for the next kind of question that I'll ask you, I will basically tell you how many times you're drawing. So if you draw 2 cards from a deck of cards, let's do 72,000 times. How many times will the total be 20? I'm going to actually change the way I worded this question, but that's fine. I can word it that way. But I just want to show you a different way I can word this. Okay, so I can say if you, so this is totally fine, but now I'm going to change it. If you play 72,000 hands of blackjack. So I could ask the question that way. It's just a slight variation on what I just asked. Now, if you don't know blackjack, I understand. But in blackjack, they basically give you 2 cards to start anyway. So I can say, if you play 72,000 hands of blackjack, how many times will you start with a total of 20? So it's just a different way I can ask the question. Okay, anyway. So again, to figure this out, what you have to do is you're going to multiply the probability times how many times you did whatever you're doing. So here's the probability. Let me go ahead and write it down. So it's 10.26, oops, 10.26%. Now you're supposed to convert this to a decimal. What you do first is you erase the percent sign. And then the decimal point, you have to move it 2 times to the left. So I'm going to erase it and go 2 times to the left. And that's where the decimal point is. So 10.26% as a decimal is 0.1026. Okay. Then you're going to multiply that by 72,000 times on the calculator. Let me do that real quick. 0.1026 times 72,000. I'm getting 7387.2. Now it's a little weird that we get a decimal, but even if you get a decimal, just leave it. Okay, don't worry about it. If you play 72,000 hands of blackjack, how many times will you start with a total of 20? What's the answer?
It's about 7,387.2 times.
Yeah. Again, I understand it doesn't make sense, the 0.2, but just leave it. If you don't, if you round it about 7387 times, I mean, I'll take that too. If you are worrying about it, then you can go ahead and round it, but don't worry about it. Okay, the third kind of question will say, I'm going to do the thing that we're doing in this problem infinitely many times. So if you, again, I could say play blackjack, but let me just go back to drawing 2 cards. So if you draw 2 cards from a deck of cards infinitely many times, so I'm not going to, I'm going to go back to a percent. When I say infinitely many times, I'm always going to ask what percent. What percent of the time will the total be 20? Okay, what's the answer?
Exactly 10.26% of the time.
Just like that. Perfect. Okay, that's the second example of many that we're going to do. Any questions on this one? Oh, sorry, this should say number 2. Sorry, guys, this is our second example here. Okay, so let's go ahead and do a third example. So we'll call this 3A. So now I'm going to go and look at the third experiment that we did last time. So let's pull that up here. So the third thing I had you guys do was you were trying to figure out the probability of rolling a total of 7 when you roll a pair of dice. So the experiment was you're going to roll a pair of dice. But again, we didn't actually have physical dice. We simulated it online. But still, imagine the idea is you're trying to figure out when you roll a pair of dice, what's the probability the total is 7. So you roll it a bunch of times. The experiment is rolling a pair of dice. The event is after you roll, what do you care about? You care if the total is 7. Whatever you're trying to find the probability of, that's what you care about. And let's go ahead and take a look at this data over here. Again, this is one student's data, but again, I have it all written over here. This is all, by the way, in the miscellaneous link if you want to look at it later. Okay, so the experiment is rolling a pair of dice. The event was the total 7. This student, the first time, total wasn't 7. Second time it was. Third time, anyway. So the ones mean the total was 7. The zeros means it wasn't. And here's the percentage of times the student got a total of 7 so far. It was 0% after the first roll, 50% after the second, 33, 25, 20. And if you watch the numbers, again, what happens at the beginning? It jumps up, they move around a lot. It goes from 0 to 50, then down to 33, 25, 20, 16, 14, jumps up to 25, then it's going down again. But as you go down more, as the more times you roll, these numbers don't move around as much. The more times you roll, the less they're going to move around. This student's guess at the end of 25 rolls was 16% is the probability of rolling a total of 7. Now, the actual probability is 16.66666%, so that's a really good guess. But again, if you don't get that guess after 25 times, it's totally understandable because you only rolled 25 times. Let's go ahead and take a look at the picture. This picture, for just 25 times, looks really good, and they should all look like this, again, if you roll enough times. But it's a little bit of a coincidence that it happened after just 25 times. So let's take a look at what's happening again. So the red line is the actual probability of getting a total of 7, which is, so how high it is, the height of it is the probability, which is 16.7%, whatever. And then the blue graph is the percentage of times we got a total of 7 so far. And as you go to the right, you're rolling more times. So the first roll was 0, and the second roll was up to 50%. And the height of it, the height is the percentage of times you got a total of 7 so far. So as we go up and down, we're trying to level off. And you see it's trying to level off, and it's trying to hover around the red line. See, it's a little bit above, then a little below kind of thing. So that graph looks really good for just 25 rolls. But anyway, to get a better graph, you want to roll way more than 25 times. So again, I took all the data from all the students, and let's scroll down. And this whole scrolling down effect, I told you guys to calculate all these probabilities. And the reason is because I want you to scroll down with your eyes and see what's happening. And as we scroll down what's happening, the numbers are trying to settle down. They're trying to stabilize. They're trying to head towards this number 16 point, whatever it is. They're trying to head to the actual probability. It's just going to take some time to get there. Here, let me go faster. So look at the numbers. So they're in the 15s now, 16s. Okay, we're back in the 15s again. But you're not going to see 50% like we saw earlier. You're never going to see that again. So the best guess after all the data that I had 1,179 rolls from all the students, and I did a few of them too. The best guess was 15.9%, which is pretty close to 16.66%. It's not exact. It's not, and if someone wants to say no, it's not not that close, well then the answer is you want to get closer, you have to do it way more times than 1,000 times. And if we look at the graph, here's what the graph looks like. This graph came out pretty good. Still not the best because I'm trying to illustrate a certain point to you. And what's supposed to happen? What's supposed to happen is the blue graph, which is the percent of times we got a total of 7 so far, is supposed to level off. It looks like it's leveling off, but it's supposed to level off to basically right on top of the red graph. I don't mean above it, I mean on it, okay? But you see, it looks like it's leveling off to a little below it. Why isn't it exactly on it? Because we didn't do it enough times. But that's roughly the idea. All graphs will look like this. They'll eventually, at the beginning, all over the place, but eventually they'll level off, and it should level off exactly to what the actual probability is. Okay, so the percentage of times we rolled a total of 7 so far is going to be very close to the actual probability, which is 16 point whatever percent, if you roll many times. Again, first few times you have no idea where you're going to be, but many times you're going to be very close to the actual probability. And the way I would ask the question would go something like this. When rolling a pair of dice, you will get a total of 7 about, how would I write it? I would write the probability of getting a total of 7 is, let's just round it to 16.7%. What does this probability mean? Okay, so again, I kind of lay out for you in that little sentence there what the experiment is, what the event is, and I give you the probability, and I'm asking you, what does the probability mean? All right, so I'm going to need another volunteer for answering this. And again, you're going to basically follow the format that's in green over there. All right, someone try to answer it.
If you roll a pair of dice many times, you will get a total of 7 about 16.7% of the time.
Yeah, perfect, just like that. I'll go ahead and write it down now. If you roll a pair of dice many times. So that's me saying if you do this experiment many times. The experiment is we're rolling a pair of dice. If you roll a pair of dice many times, you will get a total of 7. That's the event. About, make sure you put about 16.7% of the time. Okay, cool. So again, make sure you put many times. I'm missing an S here, many times. And make sure you put about, okay? Those are two things that commonly get forgotten. All right, let's go to part B. So the next kind of question, again, I would give you how many times we're rolling, and you would tell me how many times you get a total of 7. So I would say if you roll a pair of dice, let's do 180,000 times, how many times will you get a total of 7? This is the cool thing about probabilities. You can make a prediction as long as you do something enough times, okay? If you only do it a few times, If I say we're going to roll the die 5 times, how many times are you going to get a 7? Then I have no clue. Okay, but if you were really to roll a pair of dice 180,000 times, I'm going to be almost certain how many times you got a total of 7. Okay, so again, the way you're going to figure, so remember for this one, I'm going to ask you how many times. So you don't give me a percentage. You're supposed to be giving me a whole number. You're supposed to count how many times you get a total of 7. Again, if you get a decimal, it's okay. The way you do it is you have to multiply the percentage. So here's the percentage, the probability, I mean. Here's the probability. You need to write it as a decimal. So again, here's how you do it. You erase the percent sign. Then you take the decimal point and you have to move it 2 times to the left. So you erase it, and then you go 2 times to the left and put it there. So 16.7% as a decimal is 0.167. Then you got to multiply this by the 180,000 times, the amount of times you're doing the experiment. Let me do that on the calculator real quick. I'm getting 30,060. Okay, what's the answer?
About 36 or 30,060 times.
Yeah, that's how that goes. Okay, I do want to mention one quick thing on this one. So, okay, please don't forget to write about and the times, okay, about 30,060 times. If you just write 30,060, it's wrong. I need the about there, because it's not going to be exactly 30,060. The other thing I want to tell you, though, about this problem is technically 30,060 is wrong, okay? This is actually a wrong answer. The actual answer is about 30,000 times. The 60 shouldn't be there. But you know, if you write it on the quiz and you put the 60, I'm going to take it, okay? I just want you to know that the 60 is not supposed to be there, and let me explain why. Why is the 60 showing up? It's showing up because we rounded. This 0.167 or this 16.7%, this is a rounded answer. The actual probability is not 16.7%, it's 16.6666666%. Goes on forever. So the little bit of rounding created this little 60 that shouldn't be there. But again, don't worry about it. You can leave it there. I just want you to know that the correct answer is 30,000 times. If you take the actual probability as a fraction, I do that in the video that you guys watched last time. It's 1 out of 6. If you multiply 1 over 6 by 80,000, you're going to get 30,000. The 60 won't be there. Okay, so the 60 is just appearing because of a rounding issue. So it really shouldn't be there. But again, I'll take it as an answer if you give me an answer like that. Well, let's go to the third one. The third one is going to say if you roll a pair of dice infinitely many times, what percent of the time will the total be 7? All right, so that's how that one goes. And again, if I say infinitely many times, I'm not going to ask how many times are you going to get a 7. I'm going to ask what percent of the time will you get a 7, and what's the answer?
Exactly 16.7%.
And then right of the time, yeah, exactly 16.7% of the time. So this question, you have to put the word exactly in there. Now you might go, wait a minute, Greg, 16.7 is rounded, so why should I put exactly? Don't worry about that. Just make sure you put the word exactly, okay? Even if this is rounded, we're not going to worry about the rounded part. Okay, that's number 3. Any questions on number 3? All right, let's keep going. So we did 3 experiments last time, but we're going to do some more examples. So I have some more experiments. Another thing I wanted people to do, but we didn't do it. This is what I would have loved. You know, I really like this idea of doing it many times and seeing, you know, what the actual probability is. So what I would have wanted you guys to do is flip a coin. So we're going to do this flip a coin example now and figure out the probability of the coin landing on heads. Now, you know the probability of a coin landing on heads, but I want you to figure it out by flipping it a bunch of times. What I wanted is for students to flip the coin 10,000 times. But I know no one in here is willing to flip a coin 10,000 times. So what I did was I simulated it for you on Excel. So I have this also in the miscellaneous link so you can check it out. I have a whole description of what's happening here. But the experiment is we're flipping a coin. That's the thing we're doing. And the event, the thing I care about is does a coin land on heads? The probability of coin landing on heads is 50%. We already know that. And now we're going to take a look at these numbers and see what happens. So Excel is simulating flipping a coin. And it got heads the first 5 times, then tails the 6th time, heads, tails, tails, like that. And each of these numbers on the right is a guess of the probability that the coin will land on heads. Our first few guesses is 100%, which we know is a bad guess, but it's just the first few flips. And then now we're getting some tails in there. Oh, we got exactly 50% there. Now it gets lower, then higher. Anyway, as you scroll down, it's a better and better guess of the probability that the coin will land on heads. So I'm going to scroll down. I'm going to scroll down kind of fast here because I have Excel doing it 10,000 times. 10,000 times, I think everyone in here would agree, is a lot of times. But I want you to watch as you scroll down. Look at the numbers. They're all in the 49s and 50s. You know, it's never going to get to 52. It's never going to get to like 47. It's in the 48s over here. But again, it's trying really hard to get to the right answer, which is 50. But you might have to go a while to get there. So, okay, this is taking too long. Let's scroll down faster. Okay, at the end of 10,000 flips, let's see. Okay, let's go down slower. So take a look at these numbers. They're all in the 48s. The Excel's guess at the end is 48.98% is the probability that the coin will land on heads. Now take a look at this picture. This picture is really good. It's still not perfect, but it's really good. Again, the red line is at 50%, which is the actual probability that a coin will land on heads. The blue graph is the percentage of times the coin landed on heads so far as we're flipping. At the beginning, it's all over the place. It's a little hard to see because we flip so many times, but it's moving around. But if you look at the right side of the graph, it's hard to tell the difference between the red line and the blue line. You can see it. You can see the blue. Looks like it's a little below there. But it's really hard to tell the difference because the percentage of times the coin landed on heads so far is going to be really close to 50% to the actual probability. So that's the idea. So the blue graph will eventually level off and level off pretty much exactly on the red line if you do it enough times. Okay. One other thing I want to show you real quick is if you do go to the miscellaneous link and you want to mess around with this simulation, what you can do is click on one of the cells on the right side, not the last one, but one before the last one, let's say. Now you see the mouse right now, it's a white plus sign. You guys see that? So what you do is you click on a cell and then you move the mouse to the bottom right corner and then it becomes a black plus sign like that. And then what you do is you left click and you drag down. And then when I let go, Excel will do another 10,000 flips for you. So there, it does another 10,000 flips. This time the best guess is 5.54%, 50.54%, and it'll give you another graph. You might not think this is the same, a different graph, but it is. This time if you look at the blue, it's really hard to tell the difference between the blue and the red. And the blue is a little bit above the red in some spots there, whereas in the other one was below. Let me do that one more time. So you click on a cell, the mouse is a white plus sign, then you go to the bottom right corner where it becomes a black plus sign, click, left click, drag down, and I'll do another one and it'll give you another graph. So this time, Excel's guess for the probability of a coin landing on heads is 49.68%. Again, super close to 50. And again, you can look at the graph. The percentage of times Excel got heads so far is super close to 50%. It's about 50%. All right, let's go. Let's get rid of this one. We're done with that one. All right, let's go back and answer this question. So this time the question would be like the probability of a coin landing on heads is 50%. What does this probability mean? Okay. So someone volunteer, please. Someone who hasn't volunteered yet to try to tell me what this probability means.
Okay, if you flip a coin many times, it will land on head 50%, about 50% of the time.
Yeah, just like that. Cool.
If you flip a coin many times, could I use the chances of it landing on heads is about?
No, don't use the word chance and don't use the word probability.
All right.
So you mentioned doing the experiment many times. Now you got to talk about the event.
Okay. It landing on their heads is about 50% of the time.
Yeah, so just say it will land on heads about 50% of the time. Yeah.
All right.
Okay, that's that one. Any questions on that part? Okay, so then for the second question, again, what I'm going to do is I'm going to tell you how many times we flipped. If you flip a coin, 20,000 times, how many times will it land on heads? So if you flip a coin 10 times, how many times will it land on heads? 5 times? 7 times? Could it land on heads 9 times? Yeah, it could land on heads 9 times. I can't predict how many times it'll land on heads if you only flip 10 times. I can't make a prediction. But if you flip 20,000 times, which I think everyone would agree is a lot of times, then I'll know almost exactly how many times it landed on heads. And again, the way you figure it out is you take the probability, 50%, you write as a decimal. So you erase the percent sign. If you don't see a decimal point, it's at the very end, okay, on the right side. But anyway, you're gonna have to move it. So you erase it and go twice to the left, and the decimal point goes there. So you write 50% as a decimal. Then you multiply by how many times we flipped, which is 20,000. And when you calculate the answer, you get 10,000. Now someone tell me the answer, how you're gonna write the answer.
About 10,000 times.
About 10,000 times, right? And again, it might not be exactly 10,000 times, but it's going to be super close to 10,000 times. Okay, so that's the idea. All right, that's part B. Let's go to part C. So for the third kind of question that I like to ask, it will say, if you flip a coin infinitely many times, what percent of the time will the coin land on heads? All right, what's the answer?
Exactly 50% of the time.
Exactly. And that's how that fourth experiment goes. Any questions on that one? All right, we got a fifth one we're going to do. So one more simulation. I liked that flipping the coin simulation so much that I made another one. So this time I told Excel to simulate drawing a card out of a deck of cards 10,000 times and trying to figure out the probability of getting a heart. This time Excel is drawing one card, okay, not two. I know we did an example earlier where we do two. We're drawing one card only, and we're trying to figure out the probability of getting a heart. Okay, so let's go ahead and take a look at that. Okay, so again, I have it all described over here, but the experiment is draw a single card from a deck of cards, one card, and then after you draw, you're going to look at the card and see, is it a heart or not? Because that's what I care about, is it a heart? And the probability of getting a heart is 25%. You can calculate that by hand. And actually, I think we did that in the lecture last class. But what we're going to do is we're going to estimate it empirically by running the experiment over and over again and seeing what's the percentage of times we get a heart so far. So as Excel is drawing, they didn't get a heart till the 9th draw. So on the 9th draw, their guess for the probability of getting a heart is 1 out of 9. 1 heart total they got out of 9 attempts. And again, we keep doing this, keep drawing, and sometimes we get hearts, sometimes we don't. And as you scroll down, these numbers are all guesses of the actual probability of getting a heart. And the more times you draw, the better your guess is going to be. So what's happening to these numbers? These numbers at the beginning were moving around a lot, but eventually they don't move around as much anymore. And they start settling down. Where are they headed? These numbers are headed where? They're headed to the actual probability, which is 25%. So I'm expecting these numbers to get to 25%. I'm going to scroll down faster. If you look right now, they're all like in the 24s. Okay. Might go to 23 for a little bit, but anyway, at the end of the 10,000 tries, Excel is saying, I think the probability of getting a heart is 24.28%. It's super close to 25%. But if that's not close enough and you want to get even closer, you'd have to go way more than 10,000 times. If you take a look at the graph, again, all the graphs are going to look pretty much like this, okay? The actual red graph is, the red line is at the actual probability of getting a heart, which is 25%. The blue is the percentage of times we got a heart so far. As you go to the right, you're drawing more times. At the beginning, on the left side, the graph moves up all over the place, up, down, all over the place. But on the right side, it levels off. And it levels off to the red line, even though if you look at this picture, in my opinion anyway, it looks like it's leveling off, but it's leveling off a little bit lower than the red line. But it will get closer to the red line and hang out much closer to the red line if we were to draw a card way more than 10,000 times. So in this problem, the percentage of times we got a heart so far, which is the blue, is about 25% if you do it many times. All right, so the question that I would ask you on the quiz, if it was pertaining to this example, would go something like this. It would say, when drawing a single card from a deck of cards, the probability of getting a heart is 25%. What does this probability mean?
Alright. If you draw a single card from the deck many times, you will get a heart about 25% of the time.
Yeah, exactly. If you draw a single card from a deck of cards many times, you will get a heart. Oops. About 25% of the time. Yeah. Okay. Next question. Again, for this next question, I'm going to say how many times you're drawing. So if you draw a single card from a deck of cards, let's do 30,000 times. How many times will you get a heart? Okay, so again, the way you're going to figure this out is you have to multiply the probability times 30,000. The probability is 25%. Again, change it to a decimal. So you erase the percent sign. When there is no decimal, it's on the end here. You have to move it to the left twice. You're going to put it there. 25% is a decimal, is 0.25. Then you're going to multiply it by 30,000. When you do that, you're going to get 7,500. Okay, and so you you don't have to write that calculation down, but you can. But then write the answer. So what's the answer?
About 7,500 times.
Right. Okay, and then the next question will go like this. So I'll say, if you draw a single card from a deck of cards infinitely many times, what percent of the time will you get a heart? What's the answer?
Exactly 25% of the time.
Exactly. Perfect. Cool.
Yes,
All right, so that's how that example goes. Any questions? Okay, so I'm going to show you two more examples, but the next two examples, I'm not going to go over the meaning anymore. So I'm going to tell you two stories here, two examples, but the idea is focusing a little more on empirical probability. Like empirical probability says, run the experiment many times to guess and figure out the percentage of times your event occurred so far, and you're going to make a guess of the probability. These 5 problems that we just did, for all 5 of them, I knew the exact probability. So we could compare our guesses to the exact probability. And basically what we said was our guesses are going to get super close to the exact probability if we do it many times. That's basically what we learned today. Okay. But now the next 2 examples I'm going to show you are trying to figure out probabilities empirically when we don't know the correct answer. Okay. And so if you don't know the correct answer, what do? Well, you run the experiment many times. And as far as the graph goes, you have to try to guess where it levels off. And where it levels off, it's supposed to level off at the probability. And so you go, oh, it looks like it's leveling off at this number, and then that's a guess of the probability. These are really cool examples, in my opinion. I really like these examples. Let me go ahead and tell you the story. So the 6th one over here. So here's how the story goes. I used to play online poker a long time ago, back when it was legal. It's not legal in the US for the most part anymore, but back in the day it was. And here's the deal. So, you know, when you talk to a poker player, poker players all think that they're awesome. Okay, oh, I'm the best poker player, oh, you know. And I said to myself, you know what? I'm a mathematician. Math is involved in the game. Most people don't know math, and I know math. I'm going to be better than everyone else. That was my thought process, right? So I went and studied a lot, got a lot of books, thought about a lot of things, and I would play poker with friends, and I would do okay. I'd go to the casino once in a blue moon and play poker and do okay. But then when I played online, I lost all the time. So I was like, what the heck's going on? Why am I losing all the time? A friend of mine said, hey, it's rigged, you know, it's all fixed. And I thought, you know, that's like a cop-out answer. It's like, That's easy thing to say. It's rigged, you know. It might be rigged, but the thing is, maybe it's not. Let's see if I could figure out if there's another reason, you know. So I was trying to figure out, okay, what level am I online? Maybe I'm just not good enough to play in the game that I was playing at. So I decided to play in the cheapest game possible. Because if I'm good at all, then I should at least be able to beat that game. Okay, beat the worst players kind of thing. And the worst players are going to be at the cheapest games because if you think about it, if you're a good player, you want to make money, so you're going to play at higher level games, higher stakes games. So I designed an experiment. And the experiment goes like this. So I played at the cheapest game possible. If you don't know what blinds are, that's okay. But at this game, the blinds were 1 cent and 2 cents. So that's pretty much the cheapest it gets, okay? And I designed an experiment, and the experiment went like this. I would go to a table online, and I would start with $1.50. And I would keep playing at the table until I either doubled the money, so until I won $1.50, or until I lost my $1.50. So I'd either have to make a profit of $1.50 or I have to lose all my money. But I keep playing and play real hard and try my best until I either double my money or lose it all. And then what I wanted to figure out was, what's the probability that I double my money? So to figure out that probability, I have to do that over and over again. So what I did was I did it 100 times. I went to 100 different tables. It took a long time. And every single time when it was over, I wrote down, did I win or did I lose? You know, did I double my money or did I lose it all? And I'm trying to figure out the probability I double my money. Now, if I'm a winning play, so okay, if the probability I double my money is 50%, that means that half the time I'm doubling my money, half the time I'm losing all my money. So I'm basically a break-even player. I'm not a winning player at that game. I'm not a losing player at that game. But if the probability of doubling my money is higher than 50%, then I'm a winning player at that game. And I'm hoping at least at that game I could be a winning player. So I want to go ahead and show you the results here. The reason I really like this example is because how could you calculate the probability I double my money? I mean, oh my God, it's like impossible. Because, you know, every time I play at a different table, I'm with new players, you know. I mean, there's just so many things. There's no way you could calculate it. So the only way you could do it is play a bunch of times and see what's the percentage of times that you double your money. Okay, so now let's take a look at this. Now, I did have to do some weird math over here. This first probability, all the probabilities, for some reason I wrote them as decimals instead of percentages. This is 162%, this first probability. Now you're gonna say, wait a minute, Greg, probabilities can only be between 0% and 100%, so you're pulling some weird stuff there. You're not allowed to do that. Again, I had to do some weird calculations. Let me explain why. Because it's almost impossible to exactly double your money, okay? On the first table, I didn't win $1.50. I won $3.38. And then you might say, okay, Greg, you weren't supposed to play until you won $3.38. You were supposed to, as soon as you win $1.50, you're supposed to stop. And so let me just tell you what happened. What happened was, you know, the hand before the last hand, I must not have been up $1.50 yet. But then the very last hand, me and maybe a couple other players must have put a bunch of money in, and then I won the hand. So I won more than $1.50. So I have to take that money into account, the fact that I won more than $1.50. So because of that, I had to pull some weird math. It's explained up here, but don't worry about it so much. So second table, I won $2.36. Again, I was supposed to stop at $1.50, but I won a little too much. Third game, I won $1.75. Fourth game, I won 99 cents. Now you might go, wait a minute, you weren't supposed to stop if you only won 99 cents. I think for that table, what happened was I was up 99 cents and then everybody left. So the table was over, so I had to just write that down. Then things start looking normal. I lost $1.50 here. I won $1.51. And anyway, and these numbers here are all guesses of the probability that I'll double my money. Okay. And what I want you to notice is, look, it started at 1.62%. I mean, I'm sorry, 162%. And now it's down to 67%, 70%. It's moving around. And the more times I do it, the better guess I get at the probability that I'll double my money. So now I'll show you the graph after 100 times. So here's what the graph looks like. Okay. And again, take a look at what it looks like. At the beginning, it's all over the place. It's up here, it jumps down, it's moving around. But as you go to the right, the more times I do it, it looks like it's leveling off. And again, the cool thing about this is I don't know the actual answer, but from this, you can make a guess. So tell me, what's the guess that I will double my money in this experiment here? What's the guess? What's your guess? No one knows? So you're basically trying to guess where is it leveling off, at what height is it leveling off. So you see it's leveling off. You go back here to read the number, and it's 0.6. So the best guess that I'll double my money is 0.6 or 60%. Okay, so that's the idea. I'm not trying to brag that I was a winning player. Okay, in the end, I think it was like for every 100 games I win like $15. So it's not that exciting. But the exciting thing is that I could actually see what my probability is by doing the experiment a bunch of times. Okay, so be prepared for a problem, where I'll give you a graph and I say, make a guess for the probability that I'll double my money. If you were going to explain what the meaning of this 60% is in words, I'm not going to write it all down, but I'll just say it real quick in case you want to think about it. If I run this experiment many times, so if I play poker many times, I'll double my money about 60% of the time. You can write something like that. Okay, so that's an example of calculating an empirical probability where I don't know the exact answer, but I do know that the graph's supposed to level off to the exact answer. So I'm guessing that it's 0.6. Okay, we're gonna look at one more example. This last one here is about sports betting. Now, I don't really do sports betting. I have in the past, but I don't really like it because it's real nerve-wracking. You bet on a team and they're winning and you're happy, and then now they're losing. Now you're like stressed out. Then they're winning again, you're happy, and then they're losing and they're stressed out. So I don't really like to do it. But I have a friend who has a bookie and he makes bets on a website. And so sometimes I'll go on that website and I will try to analyze the bets on there and see if they're good bets or bad bets. Pretty much when it comes to gambling, don't gamble, okay? And in chapter 6, I'm going to show you guys.
I'm under 18.
Hold on one second here. In chapter 6, I'm going to show you how to analyze gambling games to see if they're good games or bad games. Pretty much just understand that every bet you could make in Vegas for the most part is a bad bet, so you shouldn't bet it, okay? But the thing is, once in a while, people make mistakes and they offer a bet that's in your favor. And if that ever happens, you should bet it and you should bet it often. If you don't want to, show it to me and I'll bet it and I'll bet it often. So anyway, so I will look for certain bets and I'll just try to analyze them, see if they're good bets or bad bets. There's this one bet that I used to make a long time ago. It's a really dumb bet, but it's if you're at a friend's watching a game and you want to have some money on it, there's weird bets you can make that I don't get nervous. I don't care who's winning or losing kind of thing. So the bet that I made back then was, it was on football and it was basically, is the game tied at halftime? That's it. So if the game was tied at halftime, you win. If it's not, you lose. That's it. So that way I'm not rooting for any teams. I just didn't really, it's just something. Stupid bet, but I wanted to see how bad of a bet it was. So to figure out how bad of a bet it was, you use the stuff from chapter 6, which we're not there yet. But in order to use that stuff, you have to first know what's the probability that an NFL team will be tied at halftime. You got to know that probability. How are you going to figure that out? You can't calculate that. So what you do is you look at a bunch of games, look at the results, and you see how many of them what's the percentage of time they were tied at halftime. So what I did is I recently updated this after last Super Bowl, and I looked at every single game from 2013 to 2019, every single game. 0 means it wasn't tied at halftime. 1 means it was. I looked at every single game, a lot of games. This took a long time. These are all estimates of the probability that an NFL game will be tied at halftime, in case you care about that probability. As we scroll down to the bottom, after how many results do we have here? There's the graph. I think it was like 1,900. Okay, 1,800 something games I looked at. Okay, and the final guess is 0.07. If you look at the graph over here, here's the graph. And again, check it out, This is the percentage of times the game is tied at halftime. It starts at 0, jumps up, moves around all over the place. But as you go to the right, it's trying to settle down. It looks over here like it's settling down at 6%, but then now it starts going up a little bit. So now it looks like more like 7%. The truth is this is still not enough data. I really don't exactly know for sure where it's settling down. But if I had to make a guess of the probability that an NFL game would be tied at halftime from this picture, I would say, it looks like it's settling down, leveling off around here. And if you go back and read the number, it's between 0.06 and 0.08. So you might say like 0.07, 7%. Okay, so that's how you can estimate a probability empirically. How else could you calculate it? Just look at all the data and see what's the percentage of times an NFL game is tied at halftime so far. Okay, so that's my best guess there. And then I analyzed that bet that I was making. It turned out it was a really bad bet, which I already knew it was, and that's the end of the story there. If I asked you to explain the meaning of this 7%, you would say something like, you want to say if you run the experiment many times, but I guess you could say if you watch many football games, or if you watch many football games, the game will be tied at halftime about 7% of the time. You could say something like that. All right, so anyway, those last two examples are just fun examples of calculating probabilities empirically when you really don't have another way to figure out what the probability is. You run the experiment many times, look at the percentage of times your event occurred so far, and try to guess where it's leveling off is basically the idea, because it's supposed to level off to the actual probability. This video is on compound events and their probabilities. Basically, what compound events are, those are ways of taking two events, remember events are lists, and building new ones out of them. So I give you one or two lists, and I show you a way to build other lists from them. Or I give you one or two events, and I show you how to build other events from there. There's three main ones we're going to look at. So in what follows, A is going to be an event or a list, and B is going to be another list. And from these two lists, I'm going to define three other lists. The first one's going to be called A or B. Normally, when we're writing a list, we give a letter to describe which list it is. So if I say A is a list, so we use a capital A for a list, or a capital B for a list. And now I'm defining a new list. Instead of giving it a letter like C or D or whatever, I'm calling it this. So this is the name of the new list. Okay, so we're starting off with list A and list B, and I'm going to form this new list called A or B. The English way of saying it is A or B. The other way is with this symbol here. This is the math way of writing it. So the English way of writing it, A or B, or the math way with a union symbol in between. You could still read that as A or B when you're reading this, or you can read it as A union B. So anyway, what's in this new list? So how do I take these two lists and build this new list? Well, anyway, this new list is the list of all outcomes in A together with those in B. Another way to say it is an outcome is going to be an A or B if it's an A or B or both. Okay, so basically the idea is, so let's say A is some list, we put curly brackets. I'm not going to list any things inside, but the things inside are in blue. And then if you have another list, B, and let's say the things inside there are in red. Then to get this new list, A union B, or again, you could say A or B, what goes in this list? Basically what you do is you dump all these things and all these things into one big master list. So you put all the blue things in the list, and you put all the red things in the list. In other words, everything in A, goes in here, and everything in B goes in here in one huge list. So just remember that A union B or A or B is a list that's bigger than both of them. You just dump all the contents of A and all the contents of B in one long list. When you do that, there's a couple issues. Some students will ask me, does the order matter when you write things down? The answer is the order doesn't matter. When you write a list or a set or an event, the order doesn't matter, so you can write in any order you want. I usually try to write things in increasing order if they're numbers, but otherwise you can write it any way you want. And the second thing is about repetition. If there's a number that's in here in A and also it's in B as well, when you write it in here, do you write it twice? Well, the answer is, to be technically correct, you can write it as many times as you want. So when you're building a list, an event, if you write the outcome, the thing on the list more than once, that's fine. It's like, imagine you're going to a wedding and you invited somebody, the same person, 3 times. I mean, that's fine. It's not the best thing to do, because the guy would be like, why did you give me 3 invitations, but so in general, you kind of only want to write things once. So my advice to you is to don't have any repetition in here, even though technically it's allowed. The main reason I think you should avoid any kind of repetition is because later on I might ask you to count how many things are in here, and when you count, you don't want to count the same thing more than once. So my advice to you is don't have any repetition in your answer. But again, if you do, For me, if I ask you to find A union B, it's okay. But if I ask you to count how many things are in A union B, then it's not okay. And the reason why this is called OR is from what it says on the bottom here. It's getting a little messy. Let's erase some stuff. This line here. Okay. Well, I just crossed it out. So let's try it again. So the reason why it's called OR is because an outcome will be in here if it's in here or if it's in here. So as long as it's in here or here, you put it in the new list. Okay, so that's one way to take two lists, A and B, and build a new one, A union B. Okay, here's a second way. A and B. Again, this is a new list. This right here is the name. It's a weird looking name of a new list. Instead of me calling it capital C or capital D or something, we're calling it A and B. And part of the reason is because we're trying to show you that it was constructed from some other list. So A is a list, B is a list. We're building this new list, A and B. The math notation for it is this right here. You can read that as A and B, just like you read this as A and B. Or you can read this as A intersect B, because that symbol right there is the intersection symbol. So A intersect B. Anyway, what's in there? Basically, it's the overlap. It's any outcome that's on this list. So if an outcome is on this list and it's also on this list, then it goes to this list. So it's all the things that are on both lists. You have to be on both lists to be on this new list here. So A and B is the list of all outcomes that are in both A and B. So if you think of it, so you think of A as a list, and again, let me just, the outcomes in there in blue, let's say, and then you have event B, and the outcomes there in red, then what's A and B? It's this time it's going to be a smaller list. Because for an outcome to be in A and B, it's got to be in both these lists. So I'm going to basically shade it purple. The idea is that if an outcome is in A, that means it's painted blue, and it's also in B, so it's painted red, then it's got to be painted purple. So it's got to be, one more time, in both lists. So you look here and you go, so you see all the outcomes here, then you see all the outcomes here. If you see anything that's on both this list and this list, then it goes in that list. Okay, and then a third one is called not A. So the English way of writing this event is not A. So again, this is a symbol for a new event. Oh, by the way, for this event, you only need one event. So you only need to start with one event. For this one, it's like if I give you this event and this event, or these two lists, then you could build this one. For the second one, same thing. If I give you the list A and list B, you can build this list A and B. But for this one, you only need one list. So what I'm saying is, let's forget about B altogether for this example here. And if you have just the one list, A, you could build the list not A. Okay, don't even think about B, forget it. So one more time, we have one list A, and I'm going to build a new list called not A. So the symbol for it is not A, the English symbol for it. The math symbol is A with a bar on it. When you read that, you can read it as not A. Think of the bar as like not A. Or you can read it as A complement. Usually I read the symbol as A complement. So A complement or not A. And just so you guys know, our book uses a different notation for this. They use A with a C like this for A complement. It kind of looks like the C is the power on the A. It's just a different notation, and I just don't like it, so I don't use it. But I want you to know when you're doing the homework or when you're reading the book, if you see that, when they write this, they mean the same thing as when I write this. Okay, so A complement, those both mean not A. Okay, so you can also read this as not A, you can read this as not A, or the English way, not A. All right, so what's in this thing? Well, this is a list. This is the list of everything that's not on this list. Okay, so if this is the list of all males in the world, let's say, This would be the list of all people that are not on that list, so the list of all females. Now you might say, wait a minute, why is it just females? Why isn't it animals and chairs and other things? And so that's an important question. And so therefore I want just to remind you that every experiment we do has a sample space. The sample space is the list of all possible outcomes. So once you know what all possible outcomes are, usually in the book they might call that the universe. Once you know what the universe is, and you have list A, this is everything else in the universe that's not here. So if my universe is all humans, and this is all males, then this is all females. If my universe is everything that exists in the world, and this is all human males, this would have human females, all pets, all pieces of furniture, anything that's not on this list. So you do have to know what the sample space is. So that's why over here I have it written as, this is the list of all outcomes that are in S. They have to be in S to be here, but they have to not be in A. So you list everything not in A, but make sure whatever you list is in the sample space. Okay, then we have a definition. Okay, so if I give you two events, I may ask you, are they disjoint? So the word is disjoint. It's also called mutually exclusive, and I think the book will use that here and there, and the online homework might use it here and there, but I usually don't use mutually exclusive in class. I just use disjoint. Okay, so two events are disjoint if there's nothing on both lists. So here the way I wrote it is, remember this A and B is all the stuff that's on both lists, and there's nothing on both lists. That's the idea there. When you're trying to figure out if two events are disjoint, I basically have you ask two questions. Well, actually just one question. So again, to figure out are they disjoint, you just ask yourself, is there something in A and in B? Is there an outcome that's in A and also in B? If the answer is yes, then they're not disjoint. So disjoint, so the answer to this question and disjoint are opposite. So if there is something in both A and B, if the answer is yes, there is, then the answer is they are not disjoint. Disjoint means there should be nothing in both. So if the answer is no to this question, then the answer is they're disjoint. So that's usually the way I do it. So, okay, so one more time, you ask yourself, is there something in both events? If the answer is yes, then the answer is no, they're not disjoint. When you ask the question, is there something in both A and B? If your answer is no, then the answer is yes, they are disjoint. Okay, so let's do a whole bunch of examples. Okay, in this example, the experiment is that we're going to roll a die once, and we have all these events, A, B, C, D, and E, and I'm asking you to find these other events. So these are events that could be built out of these events. Okay. So I'm going to start off with finding these two, so A union E and B union D. Actually, what I'm going to do is I'm going to write down what these events are first. We've done it already in class, so let me not spend the time on it. Let me just go ahead and write them down. So since A is the event, the die lands on an even number. Remember, we're rolling a die, so maybe I should write up here what the sample space is. It's 1, 2, 3, 4, 5, 6. So whenever you list things, don't list anything that's not on that list, because this is the master list. This is the list of all possible outcomes. So die lands on an even number, it's just the even numbers that are on that list, so 2, 4, 6. Like, for example, if you're not paying close attention, you might list 8, 10, 12, but those numbers are not on the die, so you don't list them. It has to be a number that can be rolled on the die, since that's what our experiment is. Okay, die lands on a multiple of 3, so that's 3, 6. Die lands on a prime number, 2, 3, 5. Die lands on the number 4, so just 4. Die lands on a number bigger than 2, so you have to list all the things in here that are bigger than 2, so 3, 4, 5, 6. Okay, so from these events here, we want to find these new events. Okay, so A union E, remember it's a list, so you're going to put curly brackets. What are you going to put in there? Since it's a union, since it's an OR, what you can do is you can take this list A and list E, which is over here. and you're just going to dump them all in one big list, which is called A union E. So I have to put the numbers 2, 4, 6 in here. So 2, 4, 6, they all go in there. And also have to make sure 3, 4, 5, 6 goes in here. And when I list them, I'm going to make sure I'm going to list them in increasing order, but you don't have to do that. And I'm going to not put the same number more than once. You see how the number 6 is there more than once? I'm not going to write it more than once. So what are we going to put? Let's see. The lowest number is going to be 2, and then 3, 4, 5, 6. Basically, that's that list, and you just don't put the number 1 in there because 1 is not on this list. It's not on this list. So you dump those lists into one master list. All right. So that's how that one goes. So one more example of an OR. B union D, or another way to say it is B or D. Remember, this is a list, so you're going to start off with curly brackets. And what's going to go in there? So we have to take everything that's in B, so here's B, everything that's in D, and dump them all in this list. And again, when you do it, just don't put any repetition, even though technically it's okay. Don't put it anyway. So what goes in there? 3, 4, 6. And again, you don't have to put an increasing order like I did there, but you know, whatever. Okay, let's do a couple examples with an AND. Sorry, give me a second to write these events again. So this was the diagonals an even number, multiple of 3, prime number, diagonals on number 4, and then number bigger than 2, so 3, 4, 5, 6. And again, don't forget the sample space is 1, 2, 3, 4, 5, 6. If you can figure out these things without writing any of these events down, that's even better, but don't make any mistakes. So if you need to write all these events down first, so all these things, if writing all these things down first helps you figure out these things, then knock yourself out. Like for example, the next example, I won't be writing them down. When should you write them down? Well, if you definitely need to write them down to get the answer, go ahead and do it. Otherwise, I don't like to write them down if they're very long. These are not so long, but if there's like, 80 things in the event, I don't want to list them all. Okay, so C and D. So it's asking you to find C and D. Remember, this is a list, so we're going to start off with curly brackets. And what goes in this list? If it's an AND, it's the stuff that are on both lists. So let's take a look at list C. Here's list C right here. And here's list E right here. What you do is you have to list the things that are on both of this list. It has to be on this list and on this list to go in this list here. And you list all the things that are in both. Well, let's see. 2, you can basically just go through this and say, well, see, 2's here, but not here. So 2's not in both. 3's here, 3 is here, so 3 is in both. 5 is here, 5 is here, so 5 is in both. And the only things that are in both are 3 and 5, so that's what you're going to list. Okay, let's do it one more time. So another AND problem. This time it's B and D. So here's list B. Here's list D. You have to list the things that are in both, so you're going to put curly brackets and then see what's in both. Well, this event has the numbers 3 and 6 in it, but this one only has number 4 in it. Since 4 is the only thing in here, 4 is the only one that has a chance, but 4 is not in here, so 4 is not in both. So nothing's in both. So I guess the answer is going to be like this, curly brackets with nothing written in between. Remember, that's empty set. In other words, there's nothing on both lists. But I don't like to write it that way, so instead I'm going to erase this. It's not wrong, though. But instead you just draw, like a circle with a line through it. That stands for empty set. Empty list. Nothing's on both lists. Okay, let's keep going. Okay, this is asking to find B complement and E complement. Once again, let me write these lists down. To save a little time, I'll just write the sample space. And I'll just write B and E, because those are the only ones they're asking us about. The diagonals in a multiple of 3, so 3, 6. And E, the die lands on a number bigger than 2. Three, 4, 5, 6. Okay. So this time we only need B to figure out what B complement is. Well, I guess you need the sample space too. So remember, this line above means B complement, or you could read it as not B. What are you going to list? All the stuff that's not in B. Here's B. Don't list those numbers. Don't list 3 and 6. List everything else, all the numbers that are not in B. But again, I understand that like the number 10 is not in B, but you're not going to put 10 here, over here, because 10 is not in your sample space. So it has to be, so whatever you list has to be in your sample space, but not in here. So not in here. So list all the things in here that are not in here. Okay, so list everything from 1 through 6 that's not 3 or 6. Remember, it's a list. So you're going to put curly brackets. And what are we going to list? Okay, let's see. 1, 2, don't list 3, 4, 5, don't list 6. Okay, and that's B complement. That's a list of all the things that are not in B here. Okay, let's try that one more time with the E complement. So again, this is a list, and in order to find E complement, you just need to know what E is. Here's E, 3, 4, 5, 6. You have to list all the things that are not in E. But again, don't look at any other events. It just has to not be in here, but it better be in the sample space. So list things in the sample space that are not in here. So don't list 3, 4, 5, and 6 from here. Kind of like take your sample space and don't list those things. So you're going to list those things. So we're going to list 1 and 2, and that's it. Okay, and then at the end of this example, there was a question. So here's the question. So 2 questions, I guess. Are the events A and B disjoint? And then are the events A and E disjoint? Okay, so let's work on this one first. So you have to ask yourself, is there something in A and B? In other words, is there something in both? Maybe just to make it a little more clear, I'll write the word both here. Is there something in both A and B? I lost it again. Let me go ahead and write down what A and B are. So A was the event 2, 4, 6. And B is the event 3, 6. So what's the answer? Is there something in both A and B? So is there something on this list and this list? The answer is yes. We see 6 is in both of them. So if the answer is yes, so the answer is yes, yes, 6 is in both. So you ask yourself this, when you're trying to figure out if the events are disjoint, you first ask yourself, is there something in both? If the answer is yes, there's something in both, then you're going to say they're not disjoint. So if it's a yes to this question, then it's no to this question. So not disjoint. Now you don't need to write all that stuff down. I want you to be doing that in your head, but this is what I want you to write down. So I want you to answer this question, all I want you to write is they're not disjoint. So I want you to go through this in your head though. So one more time, ask yourself, is there something in both? If the answer is yes, then you write not disjoint. And then I want you to write why, and I want you to write because. Whenever you're telling me, whenever your answer is no, they're not disjoint, you need to tell me why. And when you tell me why, you're going to say, because there's this thing that's on both lists. So make sure you tell me what's on both lists. So you're going to say not disjoint because 6 is in both events. Or you can write on both lists. So the purple thing is all I really need you to write. But this stuff is what I need you to do in your head to figure out the answer. Okay, so again, when your answer is not disjoint, you need to tell me why. You're going to say, but when you tell me why, I want you to tell me, give me a specific thing that's in both. Because sometimes I'll have students write, they're not disjoint because there's things in both. Well, I don't accept that answer, and the reason is because that's just the definition of not being disjoint, that there's something in both. I want you to show me that you looked at this list here and you saw, oh, okay, here's the thing that's in both. So don't just say there's something in both. Tell me what that something is. Okay, so say they're not disjoint because, and we saw in this problem that 6 is in both. And you can say in both events or in both lists, either way. Okay, let's answer the second question then. erase this stuff here. And let's see, I don't need event B anymore. We're going to need event A. Sorry, give me a second to clean this up here. Okay, so now we're answering this question. Are the events A and E disjoint? Okay, let me write down event E. Number greater than 2, so 3, 4, 5, 6. So again, when they're asking about this word disjoint, you need to ask yourself this question. In your head, you're going to say, is there something in both A and E? And whatever your answer is to this question, it's the opposite answer for if they're disjoint. So if you say yes to this question, then they are not disjoint. No, they're not disjoint. If the answer is no to this question, then your answer is yes, they are disjoint. Okay, so let's take a look. We're looking at this list, and we're looking at this list, and I'm looking for things that are in both. Is there anything in both? Yeah, you see the number 4 is in both. Also, the number 6 is in both. Now, if I ask you to find A and B, you know, this thing here. Sorry, not B. A and E. If I ask you to find that, which I didn't ask you, then you'd have to list all of the things that are in both. But when it comes to disjoint, you don't have to list everything that's in both. Just say, hey, there's this thing in both, then they can't be disjoint. So some people will say they're not disjoint because 4 and 6 are in both. That's fine. But you only have to say they're not disjoint because 4 is in both. Or they're not disjoint because 6 is in both. You don't have to tell me everything that's in both. But whatever, I just want you to know. But if it's an and, then you have to list all the things that are in both. Okay. So the answer to the question, is there something in both? The answer is yes. For example, 4 is in both. Again, you don't have to list everything. So then the answer, so that means that they're not disjoint. So since the answer is yes, there's something in both, they're not disjoint. And again, when you write the answer, all I want you to write, so all the stuff I've written down here is what you would do in your head, but all I want you to write is they're not disjoint. So everything in purple is what I want you to write. Not disjoint because 4 is in both events. Or you can write because 4 is on both lists, anything like that. Okay, let's go ahead and take a look at a second example, a second experiment. Okay, in this example, the experiment is that we're drawing one card from a poker deck, and then we have these events A, B, C, D, E, which I'm not going to list because some of them are kind of long. But then the question is asking you to build these new lists. Remember, that's what the lecture's on today, right? How to take lists and build new lists. And then there's a question at the end we'll answer later. So, okay, let's go ahead and do these. Okay, so let's start with the first one. Again, it's an OR. Remember, we're taking this list D and this list E, and we're building a new list called D or E, or another way to say it is D union E. So it's a list. So the first thing you're going to do is you're going to put curly brackets, and you're going to list the stuff. So basically you have to take everything in list D. D is the list of all the kings. It says you're going to draw a king. So I'm not going to list them all up here because these lists are going to be kind of long, all these lists here. But I want to still imagine what's in there. So if you were going to list D, you'd have to list all the kings. That means you'd have to list the king of hearts, king of clubs, king of spades, king of diamonds. List E. So you draw a card that has a number on it less than 5. So any card in the deck that's got a number on it less than 5, you'd have to list. So in other words, all the 2s, 2 of hearts, 2 of clubs, 2 of diamonds, 2 of spades. Those cards have a number on it that's less than 5. It has a number 2. You have to list all the 3s and all the 4s. So, okay, this is the list of all the kings. There's 4 things in there. This is the list of all the cards that have numbers on it less than 5. That means all the 2s, all the 3s, and all the 4s. Okay, let me write that down. This is all kings. And this is all 2s, 3s, and 4s. Has to be less than 5, so don't list the 5s. So then what's going to go in the union list or the OR list? Well, you have to take this list, all the kings, and all the cards that have numbers on it less than 5, and put them all in this huge list, in one big list over here. So you list everything together in one long list. Okay, so here's what we're going to do. We're going to write king of clubs, king of diamonds, king of hearts, king of spades, and now I've dumped all that into that list, and I have to dump all this into that list as well. So now all the 2s, 2 of clubs, 2 of diamonds, 2 of hearts, 2 of spades, 3 of clubs, 3 of diamonds, 3 of hearts, 3 of spades, 4 of clubs, 4 of diamonds, 4 of hearts, 4 of spades. And that's what's in that list. It's a pretty long list, but anyway, you just take, again, everything in D. Okay, so all kings. Put it in this list. Then you take everything in E, which is all these numbers, put them in this list in one long list. The order doesn't really matter, and just whatever you do, don't have any repetition. In other words, if for some reason 2 of clubs was on both lists, don't write 2 of clubs twice. Okay, let's try the next one. Clean this up a little bit first. Okay, A and D. Again, this is going to be a list. We're taking list A and list D, and we're going to form this new list A and D. So curly brackets. Okay, and then what are we going to list? Well, since it's an and, we have to list things that are on both lists. So here's a list. It's all the hearts. So that's the event that you draw a heart. So all the hearts. That means ace of hearts, 2 of hearts, 3 of hearts. This is all hearts. Okay, that's what this list is. This list over here is all the kings. We need to list everything that's on both of these lists, since it's an and. So it has to be on this list and as well on this list. Now, if you have trouble with the deck of cards, you definitely want to memorize what's in a deck of cards. In the lecture notes, I think I have a picture of the deck of cards, so you can go take a look, or on the website, you can check it out. But otherwise, I kind of need you to know. So we need to think, what does this list look like? What does this list look like? And is there anything on both? Well, if it's on list D, it's got to be a king. So there's only 4 choices. But if it's on this list, it also has to be a heart. So you're thinking of what are the cards that are kings and hearts? And there's only one card like that, the king of hearts. So you just list king of hearts like that. Okay, because all the other kings in here, king of diamonds, king of spades, king of clubs, none of those are hearts. So it's got to be a heart, and it's got to be a king, king of hearts. Okay, and let's go ahead and try B complement. So again, when you have an event with a line on top of it, it's the complement of that event. It's a list of all things that are not in that event. So it's a list. So I'm going to put curly brackets. Remember, you only need to know event B to know B complement. Well, what's B? All the black cards. So every card in the deck that's black is on list B. So then what's going to be on B complement? The cards that are not on this list. So the cards that are not black, which means all the red cards. Again, go ahead and look at a deck of cards if you need to, but every card is either black or red. So if B is all the black cards, B complement is all the cards that are not black, but it's got to be a card. It's got to be in the sample space. So it's all the cards that are red. That means you have to list all the hearts and all the diamonds. I'm going to run out of room here, so I'm going to write it a little bit weird. Let me write it like this. So will I run out of room? Let me see. Yeah, probably. Okay. So I'm going to list all the hearts, ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts. So 10 of hearts, jack of hearts, queen of hearts, king of hearts. And because I ran out of room, I'll write the next on the rest of it on the next line, but it should be one long list. Okay, so we have ace of diamonds. Those are red. So the hearts and the diamonds are the ones that are red. So ace of diamonds, 2 of diamonds. And yes, this list is a little long, but what are you going to do? 5 of diamonds, 6 of diamonds, 7 of diamonds, 8 of diamonds, 9 of diamonds, 10 of diamonds, jack of diamonds, queen of diamonds, king of diamonds. And that's how that goes. I'll put this original curly bracket up here. So I kind of started there, and then we ended down there. All right, so that's how you build these compound events. Let's go ahead and think about this word disjoint for this example. So there was this question at the end. It said, which pairs of events above are disjoint? So this is going to be, this is going to take a couple minutes because it's basically saying, look at all possible pairs of events. So in other words, pick any two of these and see if they're disjoint, and then do it for all pairs like that. So let's just look at, so here's a pair of events, A and B, and I want to know if they're disjoint. So I want you to take a look at this. Take a look at A. A is that you draw a heart. So this is a list of all hearts. And then B is the event that you draw a black card, all black cards. So I want you to see if A and B are disjoint. And the way you're going to do it is you're going to ask yourself, is there something on both lists? So is there something on both lists or in both events? So in other words, is there a card in the deck that's a heart and also a black card? So in that case, the answer is no. So the answer to this question is no. So are these things disjoint? Yes. Okay, instead of writing yes, let's just write disjoint. Now, if the answer is yes, it's not really much you can write. So you just write disjoint because nothing is in both A and B. There's nothing in both. So since the answer was no here, you write yes there. Yes, they're disjoint. Okay, let's look at another pair. Let's look at A with C. So we're looking at this event, all the hearts, and this one is all the red face cards. So again, you're going to ask yourself this question, is there something on both lists? So is there something that's a heart that's also a red face card? You don't need to list all of them, but if there's anything on both, then we're going to have it. So the answer is yes. There is something on both lists. And what's on both lists? Well, red face card means it's got a face on it and it's red, but I want it to also be a heart. For example, Jack of Hearts. We'll do it because it's going to be a heart, Jack of Hearts, and it's also a red face card. So yes, there's something on both. So what's the answer for disjoint? They're not disjoint. Remember, these are opposite questions. So you ask yourself this question first, and then the answer to this question, which ones are disjoint, it's the opposite answer. So since I said yes here to this question, we say no basically to this question. Not disjoint in the sense they're not disjoint. You're going to say why? Because the Jack of Hearts is in both A and C. Okay, let's keep going. Let's just do A with everything else first. Let's look at this pair of events, A and D. Okay, so we have event A here that we draw a heart, and D is that we draw a king. So this is the list of all hearts, list of all kings. So ask yourself this question, is there something on both lists? So is there something that's a heart as well as a king? And the answer is yes to this question. King of Hearts is definitely on both. King of Hearts is a heart, and it's also a king, so it's on both lists. So since the answer is yes to this question, the answer is going to be no to the disjoint question, so you're going to say not disjoint. And again, when your answer is not disjoint, write down why. Write down what thing is in both. In this case, the answer is yes. The answer is they're not disjoint because the King of Hearts is in both lists, or it's in both events, A and D. Okay, let's do A with E. Okay, so here's A. Did you draw a heart? ease that you draw a card with a number on it less than 5. So this is the list of all hearts. This is the list of all cards that have numbers on it less than 5. Answer this question. Is there something on both lists? Can you think of a card that's got a heart on it and also has a number on it less than 5? Sure, there's lots of cards like that. For example, 3 of hearts is an example of a card like that. It's definitely a heart, and it's a card that has a number on it less than 5. It's got the number 3 on it. Okay, so 3 of hearts is on both, so the answer is yes for this question. Is there something on both? Yes, the 3 of hearts. So what's the answer to the disjoint question? Opposite answer. You're going to say no, they're not disjoint. Okay, so not disjoint. And again, if you say not disjoint, you need to tell me what's on both. It's because the 3 of hearts is in both of these events, in both A and E. Okay, we have to do this for all possible pairs. Right now I've taken care of A. I've done A with everything. So let's go ahead and do B with everything now. So we've already done B with A. The order doesn't matter because I'm just saying, is there something in both? It doesn't matter which event you mention first. So I'm going to do B with everything after B. And then when we're done with that, we'll do C with everything and then D with everything like that. So every possible pair you can imagine, let's see if they're disjoint or not. Okay, so now I'm going to look at the pair B and C. Okay, so here's B, the black cards, and C, the red face card. Ask yourself this question: is there something on both lists? Is there any cards in the deck that are black and also red face cards? And the answer is no, because if it's on this list, it's black, but if it's on this list, it's red. Cards are either black or red. There's no cards that's both black and red. So the answer is no, there's nothing on both lists. So what does that mean? That means these events are disjoint. The answer is yes. So if this is no to this question, then it's yes to the disjoint question. So yes, they are disjoint. So disjoint. And again, if the answer is yes, they're disjoint, all you have to say is because there's nothing on both lists, on both, or in both B and C. If you're wording it in your head as events, you should say in both. Okay, so there's nothing in both. But if you're thinking about a list, then there's nothing on both lists. So either way. Okay, let's go ahead and look at B with D. Let me just change the color here. B with D. Okay, so here's B, all the black cards, and D are the kings. So again, you ask yourself this question: is there something on both lists? Is there a card that's a black card and also a king? Sure, there's a couple of black kings. So the answer is yes, there's something on both lists. Something like the king of spades, for example. Or king of clubs would have been another one that's fine. So the answer is yes, there's something on both lists. So since the answer is yes to this, the answer is no to the question, are they disjoint? So you're going to write not disjoint. And then you have to write down why. Give me the thing that's letting you know why they're not disjoint. It's because we know that the king of spades is in both B and D. And again, you could have wrote king of clubs. You can list them both, king of spades and king of clubs, but you don't have to. Just one thing lets me know they're not disjoint. Okay, let's look at B with E. Okay, so B is, again, the black cards, and E is that we drew a card with a number on it less than 5. So answer this question: is there something on both lists? So again, when you're trying to figure out if things are disjoint or not, you just ask yourself this question: is there something on both lists? So is there something that's a black card and also has a card that has a number on it less than 5? Is there something on both of those lists? The answer is sure. There's a lot of things like that, so yes. And so give me something that's on both lists. I don't know, something like the 2 of clubs. The 2 of clubs, since it's a club, it's a black card. And because it's a 2, it has a number on it less than 5. So yes, there's something on both. So if the answer is yes, there's something on both, the answer is no, they're not disjoint. So not disjoint. And then you're going to write down why, because the 2 of clubs is in both B and E. And again, you could just list anything you want that's on both. You don't have to write 2 of clubs. You can list everything on both, but you're really wasting your time when it comes to a disjoint question. Okay, so that's B with everything else. Again, we already did B with A. So now I did A with everything, I did B with everything. So now let's go to C. And we already did C with A. And we already did C with B. So I'm just going to do C with everything after C. Okay, so let's look at the pair C and D. And again, so we're going to ask this question, is there something on both lists? So I want to know if C and D are disjoint. So let's ask if there's something on both lists. Let's look at C. C is the red face cards. You can imagine a list of all red face cards. And D are the kings. Are there cards that are on both those lists? So again, you ask this question, is there something on both lists? And the answer is yes, because a king is a face card and a red face. So we need a card that's a red face card and a king. King of Hearts will do it. There's other ones. King of Diamonds, I guess, is the only other one. But King of Diamonds is definitely a red face card. It's red because it's the heart. It's a face card because it's the king. And is it also a king? Is it on this list? Yes. So it's on both lists. The answer is yes. King of Hearts is on both. So then the answer to the disjoint question is opposite. You're going to say no. So not disjoint. And then write down why. You're going to write because the King of Hearts is in both C and D. So it's on both lists. Okay, let's do C with E. Okay, sorry, let's change the color again. Okay, so look at list C and list E and see if there's something on both. Okay, so C is the red face cards, and E are the cards that have numbers on them less than 5. Is there something on both lists? The answer is no. Why? Because if it's an E, it's got a number on it. But if it's C, it's a face card. So face cards have faces on them, not numbers, and this one has numbers. So there's nothing that's both a face card and a number. So since the answer to this question is no, the answer to the disjoint question is yes. So they are disjoint. So disjoint. And then again, when you write why, you're just going to say, because there's nothing on both lists. Because nothing is in both C and E. Okay, so we've just done C with everything. The only thing left to do is D with everything. We've already done D with A, B, and C, so we're just going to do D with E, and that'll take care of every possible pair. Let's add it in right here. So we're doing D with E. So here's the list D, all the kings. Here's list E, all the cards that have numbers on them less than 5. Ask yourself this question, is there something on both lists? And the answer is no, because if it's on list E, it's going to have a number on it, but if it's on list D, it's a king. Kings don't have numbers on them, so the answer is no to this question. Okay, there's no king that also has a number on it. Okay, so then what's the answer to the disjoint question? Yes, they are disjoint, so disjoint. And again, if the answer is yes, they are disjoint, you're just going to write because nothing is on both lists, or because nothing is in both events, both D and E. All right, so that's how you build compound events.